any n by n matrix. So after you watch this video, you can find the inverse of a 5 by 5, a 6 by 6, a 7 by 7, whatever size matrix you want. And yeah, so finding the inverse this way is cumbersome and it's a long process. So there's another way to find the inverse of a given matrix, and I'm going to show you that in a different video. But this is the most complete definition. And to find the inverse of a given matrix A in this fashion, you need to first find what's called the matrix of minors for that matrix A. So matrix of minors. And then you also need to find, from the matrix of minors, you need to find the cofactor matrix. You need to find the cofactor matrix. And then from there, you need to take the transpose of the cofactor matrix. And I'll just write transpose, but I mean transpose of the cofactor matrix. Transpose of the cofactor matrix. And then after you've done all this, you get what's called the adjoint of the matrix that you are working with. And so the adjoint matrix. Now, once you've got the adjoint matrix, the inverse of your matrix, and again, since we're working with a matrix named A, I'm going to say A inverse. So A inverse is simply going to be 1 over the determinant of A. So this is just a number. So taking this number and multiplying the adjoint matrix of A, which is abbreviated as ADJA. Now, if you look at this definition of the inverse here for any n by n matrix, you'd notice that it's consistent with the definition of a 2 by 2 matrix that I already gave you. But in the 2 by 2 matrix, I just told you what the adjoint of a 2 by 2 is. I didn't tell you how to find the adjoint through this process. But if you chose to go through this process for a 2 by 2 matrix, you'll see that the adjoint I gave you is exactly what you'll find through this process. In other words, this definition is consistent through and through and applies for any n by n matrix, including a 2 by 2. All right. So how do we do this? Well, first, notice that when we were talking about the determinant of any n by n matrix, we talked about a certain matrix called Aij bar that we found, or we said that we can find by deleting the ith row and the jth column of the matrix A, and then having that n by n matrix that results. So Aij bar is the n minus 1 by n minus 1, sorry. So one dimension less in the row and column, right? So yeah, Aij bar is a matrix that's n minus 1 by n minus 1 that's found by deleting the ith row and the jth column of the matrix A. And so this Aij bar played a prominent role when we calculated determinants. And it plays a prominent role in defining the matrix of minors. So it turns out that if you have a matrix A that is n by n, so let's say that the matrix A looks like this, right? Like, let's say that it's like this. I need to start using a ruler, I suppose. Okay. But yeah, so if your matrix has entries A11, and then all the way through, and this would be what? A1n, and then dot, 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 and then this would be like AN1, dot, 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 and this would be ANN, right? First of all, the Aij bar definition I gave applies to every entry Aij, right? But for A11, A11 bar, as an example, A11 bar would have to equal this. It would have to equal the matrix with these entries, which is, well, so we have to cross out this first row and this first column, and so it would start with A22 and it would end with A2n in this first row, and then it would come down along its first column to AN2, and it would be ANN here. So this is the matrix A11 bar. And so similarly, think about Aij bar. So for A2 2 bar or A3 2 bar or whatever, like you similarly work with it. And so then how you get to the matrix of minors is as follows. So this is the matrix of minors for the matrix A. So matrix of minors, and this is perhaps the most cumbersome part of finding the inverse of A in this fashion, the matrix of minors, and the one that takes the longest amount of time, and perhaps also the most important. And so the matrix of minors, it turns out, is going to be this matrix here. It's going to be the matrix, sorry y'all. It's going to be the matrix, can't see, like, yeah, okay, bear with me. Okay, so it's going to be the matrix whose first entry, so in place of A11, is going to be the determinant of A11 bar. Can you imagine that? So just to find one entry of the matrix of minors, you start with a matrix A that's n by n, and then do, crossing out this and that for A11 bar to get this matrix that's n minus 1 by n minus 1, and then you have to in turn find its determinant just so that you can find one entry in the matrix of minors, which is why like this method of finding the inverse of an n by n is highly impractical and like very tedious and long a process. And so you continue in this fashion, and so you get it. So this last entry here is going to be replaced by the determinant of A1n bar. Again, that's a lot of work because A1n bar is an n minus 1 by n minus 1 matrix, and then you have to find its determinant, and so you get it. And so here you're gonna have to write determinant of a n1 bar to replace the entry an1, and then finally here at the end, if you make it here, you have to find the determinant of ann bar to replace the entry ann. So if somehow you've succeeded in doing all this, then remember that -1 to the power of the sum of I and j also played a prominent role in calculating the determinant. Well, it has an important role here also. So to go from the matrix of minors to the cofactor matrix, all you have to do is for each of these entries, calculate -1 to the power of I plus j and put it in front of each one of these. Yeah, and however many there are in between, right? Okay, cool. So we know that for this first entry here, it's going to be -1 to the power of 1 plus 1, so -1 to the second, which is +1, so we write a plus. And of course, without knowing n here, I can't comment, but it's going to be like plus minus until you get to this guy. So clearly here, if n is odd, then a1n is going to have -1 to an even number, and if n is even, it's going to be odd. So whether or not it's plus or minus here at the end, I can't say without knowing the value of n. And likewise over here, and likewise over here. But like I have a plus there, it's going to be a minus, plus, minus, blah, blah, blah. And again, I can't comment more on the sign of this entry until I know what n is, and likewise there, right? Okay. Can we say more here? If n is odd, then odd plus odd is going to be even. If n is even, it's even. So we can conclusively say what this one is going to be, right? Because then odd plus odd is always even, right? Yes. So on this guy, we can actually say it's going to be a plus for sure. But that's all we know. Okay, cool. But you just saw how to go from the matrix of minors to the cofactor matrix. And now what you have to do is... by the way, this is no longer the matrix of minors, right? As soon as I put these signs on it, it's become the cofactor matrix. So cofactor matrix. And now what you have to do is go from the cofactor matrix to the transpose of the cofactor matrix, at which point you have your adjoint matrix. Yeah? Okay, so if this is the cofactor matrix, and I guess we can call it A sub C, to say the cofactor matrix, then what you have to do is A sub C, the cofactor matrix, transposed. And that's just like, you know, taking this first row and making it the first column here and so on, right? So you should know how to define the transpose. But yeah, I haven't yet made a video defining the transpose, so I will. I was tempted to do that before I made this video, but I figured that the transpose is like such an easy definition that you weren't going to be tripped up in this video because you didn't know the transpose. So yeah, I take this guy, right? And so it's going to be positive, and it's going to be dit A11 bar to start, but it's going to end here at the bottom, this time with that guy. So it's going to be, and again, we can't tell if it's positive or negative, so I guess I could just say question mark, and question mark what? Well, the question mark is for plus or minus, right? Question mark, but then otherwise dit, and it's going to be A1N bar. Notice that I had AN1 bar, dit AN1 bar here, but I have A1N bar here, and that's because I've done the transpose. And so, you know, when we do the transpose, this very last column is going to be this very last row. And so, again, I won't know, so question mark. But otherwise, it's going to be dit, and then it's AN1 bar. Okay, sorry, I'm stepping out of the boundaries, but whatever. I always step out of the boundaries. No, and then this last guy is gonna stay where he's at, so it's gonna be plus, and then it's gonna be dit dit ANN bar, right? Okay, cool. All right, so that's the transpose of the cofactor matrix, and therefore at this point you've got yourself the adjoint matrix. So this is ADJA. And all that's left to do is take ADJA, which is this matrix here, and multiply it by the number or the constant 1 over the determinant. So you find the determinant of A, and then you do 1 divided by the determinant of A, and multiply this adjoint matrix, at which point you have the inverse of your matrix A. Yeah? Okay, cool. I don't think I need to write anymore because I already stated that once you get to the adjoint, all you have to do is multiply by 1 over the determinant to get A inverse. So that's that. And obviously this was all a bit theoretical. Like, we didn't see any numbers here, right? Actual, like, you know, entries. And so I'm going to give you a 3x3 example in the next video. And yeah, that should suffice. Yeah? Okay, cool. Keep watching. Take care.